record it here, and then I'll share the screen. And I would like to bring to your attention that I was able to record the lecture. So you'll find it in the option on the web page itself. And you'll have to find the recordings. Hopefully this recording for today will also work here. That is the summer 2023 2-hour lectures. There are recordings of the 1-hour lecture from the last semester. I'll leave them until we succeed in basically adapting to the new version of Zoom that we are using right now. Last lecture, we took an overall view of the energy picture in the world. We made the point that the future or the vision of future energy production is a combination of renewables and nuclear energy. The fossil fuels are, in fact, dead animals and dead plants that have been based on solar energy, which is a nuclear process, by the way, of course, fusion in our star, the sun. However, this option is being depleted. It's not going to be there in the long-term future. So that is the interest in nuclear energy production in general. So if you go to the list of assignments here, you'll find the assignments that you have to submit to the Canvas site here, canvasillinois.edu. And I would like to warn you about a possible resurgence of the COVID-19 in the form of a new version. They call it a variant, they call it XBB.1.5. We are lucky that we are on the internet. Here is the assignment for today, and it says that we are going to cover the chapter on the first human-made reactor and the birth of the nuclear age. An interesting aspect of the situation we have is that none of the attendants, including their parents and including the instructor himself, were born when that nuclear age was born. So it's a very interesting kind of history that we need to learn about. Going back to our class web page here, we start the chapter in the notes here on the first human-made reactor and the birth of the nuclear age. All right, so how did the nuclear age, how was it born? And it was born, obviously, in the Chicago pile number 1, designated as CP1 reactor. Interestingly enough, that was an event that happened here in our state of Illinois at the Stagg Field at the University of Chicago. And at that time, where of the Chicago pile number 1, the participants sent a message to Washington, D.C., and the message here, I'll quote, unquote, you will be interested to know that the Italian navigator has just landed in the New World and the natives are friendly. Obviously, it was a quoted word and message. The Italian navigator referred to was not Christopher Columbus, but back again to Enrico Fermi that we mentioned in the last time. I would like to add the host here, so I'll stop sharing and come back to adding the host, co-host, to help me answer question in the chat room. Alvaro, thank you for joining us. So I'll share back again. So the coded message meant that whatever endeavor they were involved in was successful. And remember, the Enrico Fermi was a genius, and we mentioned last time the Fermi paradox and the naming of the large laboratory by Chicago after his name. Nobody was able to take pictures at that event, but a painter provided us with a painting of what went in that event. And the painter was Gary Shahan, and he reconstructed the event. He shows here Enrico Fermi, who was the leader of that whole group, and he shows it. He shows the group in a squash, basically enclosure here, and they are on the on a kind of high port, and in front of them you could see that they had a pile of what? A pile of graphite. Now, what is graphite? Graphite is a common material, and it's used in our lead pens. Like when you use a lead pencil, you're not using lead, you're using graphite. Now, graphite is, of course, carbon 12, and it's black in color. It has very interesting properties, as we learn later, is that it helps moderate the energy of the neutrons. And the genius of Enrico Fermi was that he understood that to cause fission at a high rate, you need to slow down the neutrons from the energy at which they are born. And they are born at an energy of 2 million electron volt. That's another unit of energy that we have to try to learn. 1 electron volt is the energy acquired, kinetic energy acquired by an electron when it falls through a potential of 1 volt. So 1 million electron volt would be 1 million the kinetic energy of a neutron born in fission. Actually, the neutron born in the fission process comes out at 2 million electron volts of energy. I'll give you an assignment on this today. And the graphite here helps reduce the energy through collisions, because the neutrons that are born from fission interact with the nucleus. They do not interact, they are neutral after all, with the electronic cloud around in the atom. So the neutrons would hit the nuclei of the graphite, lose their energy all the way down to 0.0025 electron volt. And at that energy, that fraction of the energy at which they were born, they are more efficient at causing fission. And that's why they had that huge pile of graphite. We'll learn later that they're trying to give it the shape of a sphere, because in that case, they get what's called the minimum critical mass. The pile of graphite was surrounded by some kind of wood to keep it in place. And they had here some rods that came into the in and out from the pile. Those rods were made out of steel, and steel, iron in that case, absorbs the neutrons. So as you insert the piles in, you shut what we call the chain reaction. If you withdraw them out, the chain reaction increases. So that gentleman there was in charge of inserting and getting the control rods out. As a safety feature, they had a group of people on top of the pile with buckets that contained boron. Boron has an interesting property, especially boron 10, is that it's a very strong absorber of neutrons. So that group there on top of the pile was in charge of a safety feature. If something would go wrong, then they would dump the buckets of boron, actually boric acid, or balls of boron, so that they shut down the chain reaction as a safety feature. The whole thing was also enclosed in a large, another safety enclosure of basically the fabric of a Goodyear balloon of all places. The fascinating thing is that Chicago pile number 1 contained all the elements or the parts of a modern day nuclear reactor. It had the graphite as a moderator. Inside the graphite, they had the fuel. And the fuel in that case, as you know, is uranium. It was balls of uranium. And we'll see later that part of the genius of Enrico Fermi is that it didn't have a slurry or some kind of a mixture of graphite of uranium. Instead, he had them separated for a reason that will become clear later. So the components are the fuel, the uranium, the moderator, the graphite, the control rods to control the reaction, and the safety features. And these are the same components in modern day nuclear reactors producing electricity, producing energy that could be used for desalination also, or getting fresh water supplies for the world. And except that modern day reactors, instead of using graphite, use instead water. Sometimes some designs that we'll study later use heavy water. Instead of H2O, we use D2O, where D is the isotope of hydrogen deuterium. So the same components of that power of the Chicago pile #1 reactor are parts of modern day reactors, except the power produced from that pile was a very, very, very tiny half a watt of energy, half of 1 joule per second. Whereas in the modern day reactors, the power we produce has reached the level of the thousands of megawatt, or the gigawatt, 10 to the 9th watts. Watts, of course, is a unit of power, not a unit of energy. 1 watt is 1 joule per second. So from 1/2 of a watt in the Chicago pile #1, humanity is now producing power from nuclear processes at the level of the gigawatt, or the billion of watts. So that was the success, and that happened historically on December 2nd, 1942. As I said, nobody in the audience or even the instructor were born yet at this time. Enrico Fermi was an experimental and theoretical physicist. He was born in Italy in 1901. He taught theoretical physics at the University of Rome in Italy. He was a co-inventor with Leo, another gentleman of interest that we'll talk about later, of Leo Szilard. Leo Szilard was a Hungarian. At the time of 1942 here, the winds of war were blowing in Europe, same as the situation today. Interesting enough, 70 years later, the Europeans are at each other's neck back again. And from the nuclear perspective, we face the big danger or the risk of global war, global nuclear war that can cause the end of our technological civilization. Hopefully it will not happen, and basically people sanity will prevail in the whole world. He had received the Nobel Prize in Physics in 1938 on the absorption and diffusion of slow neutrons. See the word here, slow neutrons. He slowed down the neutrons, and because basically he was the director of the project, but he's the one also who warned us about the possible end of our civilization by those filters that we talked about last time. It happened at the west end of the Stag Field in one of their squash courts, and it was in the afternoon at 3:25, and they sent that a message to Washington telling them that they succeeded. This is Enrico Fermi, our hero in that case. He helped us basically build the first reactor ever based on his knowledge about the behavior of neutron physics. The winds of war, as I said, were blowing in Europe in that period of 1939, 1940. And he chose to come to the United States with his wife. And he was basically got involved immediately in what was a code word for it, the Manhattan Project. The Manhattan District Project, actually, in short, the Manhattan Project, had an objective to build an explosive fission device. Starting in 1942, two test piles were built at the Stagg Field in Chicago. And by November 1942, they had constructed the lattice of carbon blocks in the form of a graphite cube. Again, graphite is really the element carbon, and it contained lumps of uranium in the form of sphere. And I'll have a picture for it right here, and I'll come back to it. So this is the 10th layer of that part. This is an actual picture. You could see here he had blocks of that graphite, and it contains balls of the fuel, in that case, natural uranium. I'll try to cover the topic of the competition between the United States and Germany. As you know, the fission process was discovered in Germany. So the United States learned about it, and there was a fear that the Germans would develop a nuclear device from the huge energy that's released in a fission process. So the United States started that so-called Manhattan Project. Now, the Germans, in their approach to causing fission, used initially, later on, they used that form of a separate uranium from graphite, but initially they started with a slurry of uranium in heavy water. And that was not successful in creating a self-sustained chain reaction until later on they used cubes in heavy water. So heavy water was their moderator medium instead of the graphite. As I suggested, the energy of the neutrons is born at 2 million electron volt of energy. And the graphite, or the heavy water in that case, reduces the energy of the neutrons to become in thermal equilibrium with the medium in which they are moving. And the thermal equilibrium, of course, in that case comes from thermodynamics. And we are going to call this in a moment the KT energy, or the KT neutrons. Now, the neutrons are born at an energy in fission from an energy of 2 million electron volts. And the interaction with the graphite or any other moderator like water or heavy water or beryllium, another element, you take the ratio of 2 million electron volts to the thermal energy of 0.025 electron volt. So you reduce the energy of those neutrons by a factor of 80 million times, 80 million times. And it was known at the time that the fission process, according to Enrico Fermi, has a larger cross-section, or is more likely to occur in the rare isotope of uranium. There are several isotopes in nature of uranium. We'll cover that today. The isotope uranium-235, not the more common isotope that is uranium-238. And the reason is that the process is more like a quantum mechanical process rather than just a classical mechanic process where you think that, oh, a higher energy neutron will fission the uranium-235 or break it apart with a release in energy in the difference of mass between the product and the reactants. You'll find that that 2 million electron volt of energy, if reduced to the 0.025 electron volt, leads to a higher probability of the interaction. You can think about the nucleus as being a potential well, and as the neutron comes in as a wave, it has a higher probability of being absorbed or falling into the potential well when it is at low energy. So the moderator becomes a very important aspect of the process itself. Some gentlemen who took our class here had his father work on the project, and he provided us with that nice picture here, Paul Mickels, of one of those graphite blocks. You could read here, that's a historical graphite from Chicago pile number 1, first nuclear reactor, December 2nd, 1942, at the Stagg Field, the University of Chicago. So that was a historical event that happened in December 2nd, 1942, the first ever self-sustained chain reaction. The Chicago pile number 1, of course, was designed and built at the time of where war was on the horizon. So they kept the process secret, but they patented it. And this is a patent of the Chicago pile number 1. If you go to the patent office, you find patent 2,708,656. They filed it after the war, obviously, in 1955. This is a patent showing the pile itself and showing the control rods that would control the chain reaction. Nuclear reactors today, of course, are controlled by the same process of inserting control rods that would absorb the neutrons and withdrawing them. Then the chain reaction proceeds and the fission process occurs. Now we have to become a little quantitative here and distinguishing between fast neutrons and thermal neutrons and intermediate neutrons, because when neutrons are at different energies, they have different properties. Now, from thermodynamics, the kinetic energy of neutrons in thermal equilibrium with the moderator, like the air molecules are in thermal equilibrium in the rooms that we are sitting in right now, is of course described as kT. Now, K is the Boltzmann constant, 1.38 10 to the minus 16 erg. Erg is another unit of energy. It's not the electron volt. The erg is a unit of energy used in the conventional system of units. So ergs per Kelvin. Now, this is not anymore designated as degrees Kelvin. It's just named Kelvin. What is the Kelvin temperature that we use in any thermodynamic processes? It's the 273 plus degrees Celsius. And we call it the Kelvin temperature, but we do not use anymore that little wiggly circle to designate it as a temperature. I'll ask you to calculate the kinetic energy of a fast neutron and as an assignment, and a thermal neutron, as well as what we call an intermediate energy neutron, using that very simple formula, the kT formula. So you know the Boltzmann constant. If you use the erg unit, you get the speed of the neutrons in centimeters per second. If you use joule as a unit per Kelvin, you get the speed in meters per second. So let us take that kT here and say, okay, that is a kinetic energy, half mv squared of a neutron. And in that case, if I know the energy E sub k here of the neutron, I can solve for V, the speed of the neutron. We call speed here because it doesn't have vectorial quantities. It moves in all directions. And basically twice E sub k, the kinetic energy divided into the mass of the neutron. And if you take the square root, because you have V squared, you find that V is equal to the square root of twice kT, because E sub k is equal to kT, twice kT over m. So if we know the mass of the neutron, if we know the Boltzmann constant, and we know the temperature, and the T at room temperature, that will give us immediately what is the speed of the neutron. And it's amazing to discover that the speed of the neutron in that case, if I substitute for K here, multiplied into T at 20 degrees Celsius, assuming that's a room temperature. So K is 1.38 10 to the minus 16 ergs per Kelvin. The Kelvin room temperature 20 plus 273, that gives me the energy in electron in ergs. I can convert the ergs unit of energy into the electron volt unit of energy by the conversion factor 1.61 10 to the minus 12, and you discover that that kinetic energy is 0.025 electron volt. So starting with a neutron born in the fission process at 2 million electron volts average energy, we reduce it using the graphite into 0.025 electron volt in thermal equilibrium with the medium. And there, the fission process or the power production becomes maximized. And as I said earlier, the graphite now in modern day reactors is substituted for by plain water. From that equation number 2, we can also calculate the speed of the neutron. We said that V is the square root of twice E sub K, the energy of the neutron divided by the mass of the neutron. You can go to Wikipedia or as we'll show it today, the chart of the nuclides or the handbook of physics and chemistry and find the mass of the neutron is 1.6 10 to the minus 24 gram. If you substitute for that 2, a thermal neutron would have a 0.025 electron volt of energy. You can convert that to joule per electron volt, 1.6 10 to the minus 19 joule per electron volt. Notice that 1.6 10 to the minus 19 is the charge of the electron in Coulomb. Convert that joule per electron volt into ergs per joule, and you find that basically the speed is 2.1 10 to the 5th centimeter per second, because we use the erg unit here, and you turn the centimeter into meters. You find that that neutron is moving at a very, very, very high speed, 2200 meters per second. And that is a thermal neutron, thermalized neutron, and the one that is at 2 million electron volt would be even moving faster. In fact, we'll discover later on that neutrons that are free neutrons out of the nucleus has a very short life, and it has a half-life basically of 10 minutes, meaning that within 10 minutes, half the neutrons that we have available to us would turn into a proton and an electron. So this is when you have free neutrons moving around, say, in a nuclear reactor. Whereas neutrons in our body, in our cells, are all not are stable. They are not disintegrating. Otherwise, we'll be fissioning all over the place. That's one of the holy grails of modern physics. So why is that so? We don't know, but we can describe it. Now, if you go for this high speed of the neutrons, you think that it is a quantum mechanical process. So here I attempt to calculate that kinetic energy using the laws of quantum, more like a relativistic the approach. So we can say that the total energy of in the neutron, using the Einstein equation that you had in high school, mc squared should be equal to the kinetic energy plus m sub 0 c squared, the rest mass energy. From this, we can calculate really the kinetic energy of a relativistic neutron. So it becomes the difference in mass between the the total energy minus the rest mass energy. And that's the origin of not just writing mc squared, but writing delta mc squared, or the change in the mass between the neutron mass and the rest energy of the neutron. Beta is a ratio of the speed of the neutron to the speed of light. And from relativity theory, the mass of the neutron would be that n sub 0 here divided into the square root of 1 minus v over c squared. Now, it becomes a little complicated. I'm not asking you to go through the derivation process here, but in fact, if we adopt a relativistic kind of approach for the speed of the neutron, a 2 million electron volt neutron would can be calculated to be 1.95 10 to the 7th meters per second. This is, of course, 6.5% of the speed of light. And that justifies why we can say that the neutrons behave more like quantum mechanically rather than classical mechanics. If you take that equation of equation 2 and use a relativistic approach, that 2200 meters per second becomes 19.5 100 meters per second. In the group of the picture shown of the Chicago pile number 1, we had that group of people there on top, and their function was to scram the reactor. So there is an etymology or the origin of the word scram. Why? Because it's used in modern day computers. If some emergency is happening, the operator of the power plant would push a button to scram the reactor. In that case, all those control rods would be inserted automatically, immediately into the core, shutting the chain reaction. So that group of people here was basically were in charge of scramming the reactor. So there is an etymology there for the word scram, and it's interesting to know about it. If you visit or you become an operator of a nuclear power plant, we'll use that word. So let's look at its etymology or the origin of the word here. It means, of course, a sudden fast shutdown of a nuclear reactor. Again, Enrico Fermi coined the word, and basically that stands for Safety Control Rod Axeman. And SCRAM stands, can have an acronym, SCRAM. It was the person in charge was named Norman Hilberry's duty, and that group of people on top of the pile, if called upon, was to chop a rope with a single swing of an axe, immediately dropping the control rods, absorbing the neutrons, and shutting the fission chain reaction. These are safety features that are also existing in modern nuclear power plants. So a nuclear power plant would be composed in the same way as the Chicago pile number 1 of the fuel, the moderator, the control rods, and many levels of safety features that would shut down the reactor in case anything goes wrong, like say it's subject to an earthquake. At that time, the history of nuclear physics, when Enrico Fermi was able to start that first chain reaction, was basically, I have more detail about it in the appendix, but the main scientific milestones was first the discovery of radioactivity. And radioactivity was discovered in France by the scientist Antoine-Henri Becquerel around 1896. And you'll find that to honor him, the unit of activity, the unit is in the SI system of unit, or the Système International, is now named Becquerel. That was followed in France by a wife, Marie, and the husband, Pierre Curie. Basically, they built on the work of Becquerel by discovering the element radium, and we'll use radium later on for as a unit, the activity of radium to measure the activity again of the unit of radioactive decay, for radioactive decay in the CGS system of units, centimeter, gram, second. So here you have to deal with two systems of units. The conventional system of units uses centimeter, gram, and second, and the SI system of units uses the kilogram, meter, and second. In that case, Marie Curie and Pierre Curie discovered two elements, in fact, radium and later on polonium. The origin of the name polonium is Poland. Why? Because Pierre Curie was a French citizen, but Marie Curie married him, and they both lived in France. But Marie was initially a citizen of Poland. So the second element that they both discovered was named after Poland, polonium, Poland, polonium in that case. So here we are dealing not just with uranium as a heavy element or radioactive element, but also with radium and later polonium. And this was followed by the discovery of the electron by experiment carried in the UK by J.J. Thomson in 1897. And the energy to mass equivalence was introduced by Albert Einstein afterwards in 1905. Ernest Rutherford in the UK again conducted experiment. He bombarded a thin gold foil with alpha particle or helium nuclei, and he discovered that he developed the Bohr's model actually of the atom, where you have the most of the mass in the nucleus with the electrons having a cloud surrounding it on the outside. The neutron was discovered by James Chadwick in 1932. You could see that the progress happened quite fast here. And the neutrons now were used to bombard different elements. And in that case, you could transmute them. That was the dream of the alchemists in the Middle Ages, where they tried to convert, obviously, gold, the transition element into gold, starting maybe with lead or copper, but chemically you cannot do that. But the neutron, by altering the composition of the nucleus, we can create gold in that case. So Joliot-Curie, Irene and Frédéric Joliot-Curie, one of the daughters of Pierre and Marie Curie in the 1930s in France, basically used the neutrons to create new elements or transmutating elements. And then came our famous Enrico Fermi in Italy, who conducted experiments with neutrons, creating artificial isotopes using neutrons. In Germany, research was also being conducted there, and then two chemists, Otto Hahn and Fritz Strassmann, discovered the process of fission. They didn't know how to explain it. The fascism and Nazism was taking over Europe at the time, 1940s. And Otto Hahn and Fritz Strassmann had, actually Otto Hahn in particular, had a young lady, Lise Meitner, working with him. She left Germany to England, but she continued corresponding with basically her co-worker, Otto Hahn. He related to her that he bombarded uranium with neutrons and somehow found elements in the middle of the periodic table, like barium, for instance. She was smart enough to explain the process in terms of a very simple model of the nucleus of the atom splitting into two parts, and that the electrostatic repulsion that she calculated from just a Coulomb energy repulsion between the two products of the fission process can lead to tremendous amounts of energy release. In that case, a fission event can produce 200 million electron volts of energy, single fission event. Compare that 200 million electron volts of energy release from fission of the fission of neutrons to the ionization energy of hydrogen. Ionization energy is the energy you need to separate the electron from around the nucleus of hydrogen, and that is only 13.6 electron volts, not 200 million electron volts. So here we have fission going up many orders of magnitude higher in energy release than the discovery of fire. So the discovery of neutron and of fission energy release is another discovery of humanity beyond the discovery of fire. That energy can be harnessed, of course, for great benefit. Also, Lise Meitner, in fact, calculated it and immediately communicated it to other scientists like Niels Bohr in Norway and other scientists. And the idea came into the United States is that, that fission process can be used, of course, in a controlled state. Obviously, it can be used to great benefit. You can produce electrical energy as it's used today. You can dissolve water, turn fresh water, salty water into fresh water desalination from the salty oceans. You can use it to ship and rocket propulsion. It can produce isotopes for nuclear medicine. You can excavate harbors and canals, like a new maybe Panama Canal that is sea level rather than using locks and dams. You can also use it as a defense against comet and astral assailants, which is another one of the filters that we mentioned for humanity, and any other uses requiring energy densities far exceeding what we can get from chemical energy. So that was the background in the process itself. So as Lise Meitner worked with Otto Hahn in Germany, she corresponded with him when she left Germany, of course, escaping like what's happening today. Many people are escaping Russia and escaping the war, Ukraine and so on. She went to England and she reported the results to Niels Bohr, another scientist in Norway. He fully understood the implications and immediately communicated the findings to scientists and researchers in England and the United States. One of them is shown here in that picture, Leo Szilard, and you recognize here Albert Einstein. This is a reenaction of what they did. They sat down together and wrote a letter, and they addressed it to President Franklin Roosevelt in 1939, and they warned him about fission being discovered in Germany, that Germany could use it for creating a device for war in general. So they wrote a letter to President Franklin Roosevelt and urging him to initiate work on the possibility of the Germans building an atomic device. President Roosevelt immediately established what was called the Manhattan Project, and the goal was to beat Germany into building that nuclear device that would release nuclear energy. In the UK, a similar process was established in what they call the military applications of uranium disintegration. They called it the MOD Committee. And the Army's Manhattan Engineer District Project, or Manhattan Project in short, was established in the United States under Brigadier General Leslie Grove. Now, General Leslie Grove was famous at the time for being the civil engineer from the Corps of Engineers who built the Pentagon building. So he was given the process to investigate what the Germans are trying to do and beat it in the United States. As a part of this project, the work was initiated at the University of Chicago Metallurgical Lab under another scientist, Arthur Compton, in 1942. And the end of this, all these new discoveries in science and knowledge about nuclei and the fission process culminated in what we are covering today as the Chicago Pile #1, designated as CP1. That was followed later on by building another pile in what became today the Argonne National Laboratory in the United States by Chicago in general. Now, here we are talking about many different elements. We talked about graphite, which is carbon. We talked about uranium, and we talked that uranium has different isotopes. So we talked about water and heavy water, and the information in that case comes to us not from the periodic table of the elements. It comes to us from what we call the chart of the nucleus. So before proceeding further, we are going to stop and go back and get to in the parlance of the information age, what is our data warehouse so that we can mine it for data. And in that case, let's first look at some sources of information that we get in our calculations, engineering calculations. And you go to our link here in the web page on the nuclear data for the isotopes and elements. There are several links there that you can choose. This is the Los Alamos National Laboratory periodic table. So let's look at the periodic table first. And this is the famous periodic table that you have learned in your chemistry classes. You notice that we have the columns here. This is basically the number of electrons in the last shell. Here you have two interesting squares, if you want to call them this way. One of them can be expanded in a very long chain right here. In that case, we can stretch the chart of nuclides in a form that is stretched. And this is what we call the lanthanide series. It starts with the element lanthanum here. And below it, another series that we call the actinide series. Why? Because it starts with the element actinium. Now, the lanthanide series has elements like lanthanum, cerium, promethium, neodymium, promethium, samarium, europium, gadolinium, terbium, dysprosium, holmium, erbium. And these are all elements, particularly neodymium, for instance, of the new age of the where we have renewables. For instance, neodymium is used to create very strong permanent magnets that are being used increasingly in electric vehicles, as well as in even wind turbines. So these are called the elements of the renewables age. However, the actinium series contain other elements like thorium, protoactinium. That's not palladium, by the way. That's Pa is protoactinium, uranium, neptunium, polonium, americium, curium, berkelium, californium, einsteinium, fermium, mendelevium, nobelium, lawrencium, and they keep trying to discover even more elements in that case. The different colors in the periodic table of the elements, of course, refers to different series from the beginning of the field of chemistry. Say, for instance, that color is the alkali metals, this is the transition metals, this is the halogens, the non-metals, the noble gases, of course, are the last column in that case, and that would be helium, neon, argon, krypton, not kryptonite, krypton, xenon, radon, and I don't remember what's this one, ogium, I guess. So these are elements, of course, that do not react chemically very strongly. But what is of interest to us in the periodic table of the elements is that actinium series, the actinide series, containing obviously the uranium, the neptunium, and the palladium. If you want to get more information about the uranium, the chemical properties, you click there, and you get information about the atomic number, say, of uranium-92. That means that it has 92 electrons. The symbol is U. It gives us the boiling point, the melting point, the atomic radius, and that is at the Los Alamos National Laboratory. However, it doesn't give us, in that case, properties about the nuclei of uranium. To get information about the nuclear properties of the uranium, we go to what's called the chart of the nuclides. And this is what we are going to be using primarily for mining, for data in the data warehouses, in the terminology or the parlance of the nuclear age. So let us go to the first one here. This is the chart of the nuclides, or the table of the nuclides. Sometimes it's named the table of the nuclides, developed and maintained by Carey. Carey is the Korean Atomic Energy Research Institute in Korea. That's one of my favorites because they are maintaining it well. And that is basically at the Nuclear Data Center at Carey. We connect to it to get information about the nuclei properties. And let me see here. This is the table of the nuclides. I changed it from what was just last time I connected to it, previous versions of the table of the nuclides. And you could see here, it lists all the known elements, including the neutron per se. And we can go there and get information about any of the elements of interest to us. So we can go, for instance, to element 92, which is uranium. And you could see here, it shows us information about uranium. First piece of information is that it has 92 electrons. And however, uranium in nature, naturally occurring, uranium has different isotopes. And you know what's an isotope? That is basically a form of the element that has different number of neutrons, but the same number of protons. So you could see that if we talk about uranium, you have in nature 1, 2, 3 isotopes. One of them is uranium-234, one of them is uranium-235, and one of them is uranium-238. The natural abundance in atomic percentage of uranium-238 is 99.27%. This means that most of the uranium in nature is uranium-238. A very small proportion of uranium is the other isotope, uranium-235, and its abundance in nature is only 0.72%. And you can say that 1 in 140 atoms of uranium is uranium-235. Now, the interesting thing is that with thermal neutrons, it's primarily that isotope of uranium that fissions. So in that case, we emphasize the use of uranium-235 rather than uranium-238 when we produce nuclear energy. Why is that? Because it's a property of the nuclei. When they have an odd number, a value or mass number, the mass number would be the total number of neutrons and protons. When it is an odd number, that element is unstable, and if you hit it with a neutron, even with zero energy neutron, uranium-235 would fission. And in that case, we can release the energy from the difference in masses between the reactants and the product. Uranium-238 would need, because it's an even numbered isotope, it's more stable, so it needs maybe a neutron with a large energy to fission it. And I'm mentioning neutrons here because neutrons, once absorbed in the nucleus, they change the properties of the nucleus and becomes more unstable with uranium-235 than uranium-238. A much smaller proportion, 0.0055%, is the isotope uranium-234, and it comes from the decay or the radioactive process in which uranium-238 eventually becomes one of the lead isotopes over billions of years, not just millions, billions of years. So these are the naturally occurring isotopes of uranium. However, humans have created artificially more isotopes of uranium than the one that exists in nature. We can count here 4, 12, 16, 20, 24, 26 new isotopes in nature artificially. And the artificial production of these isotopes can occur, of course, in nuclear reactors. It can also occur in particle accelerators or in events where nuclear devices have been tested. So in that case, the nuclide table or the chart of the nuclides is a way for us to get information about the different isotopes. Let's look in detail about uranium-235, since this is the one that fissions. It gives us the atomic mass in 235.04 atomic mass units, and we'll define the atomic mass units in a future chapter. And it tells us about the beta decay energy. It emits the beta particles. Beta particles, as you know, are electrons. It tells us about the atomic abundance, 0.72%. And it is going to give us also information about how it decays, or the radioactivity of the mode of decay. So you notice that it gives us, it tells us that it decays through alpha decay, and we know that alpha decay is really the emission of helium nuclei to thorium-231. The mode of decay, the possible parent nuclide would be protoactinium-235 or an alpha decay from plutonium-239. That's an interesting trivia here, is that plutonium-239, later on we'll talk about it, can be produced from uranium-235, but it also can decay into the plutonium-239, decays back into uranium-235. So this is one of the elements that we can gain information about from the chart of the nuclides. From that nuclide table also, we can gain information about any other element used in the process of nuclear energy generation. So I'm asking you to go to that table, like what I'm doing now, and get me information, say, about carbon. Carbon in nature has now 2 isotopes, carbon-12 and carbon-13. Most of the carbon in nature is carbon-12, 98.89%. Remember, It is a moderator in the Chicago pile #1. Later on, we'll see that in the future, we can build gas-cooled reactors using the thermodynamic cycle, the Brayton cycle, or the gas turbine cycle, using graphite as a moderator. And these are all isotopes that have been created by man. They're artificial isotopes. The two naturally occurring isotopes is only carbon-12. So I'll ask you as an assignment to go to the table, do what I'm doing now. You go to carbon-12, we can get the weight of the isotope in atomic mass units. Notice something very interesting here. For carbon-12, it is exactly 12. So basically, it is our scale or our reference in measuring the atomic weight value, the atomic mass values. And you'll find that it is exactly 12 atomic mass units. And if we go back, we know that now it's also 98% of carbon, and that is a graphite that you use in your pencil. It is not a lead pencil, it's a graphite pencil. All these isotopes have been created by a human, in that case for carbon. Now, one of those isotopes of carbon is very interesting, the carbon-14. Carbon-14 is produced by cosmic radiation interacting with the nitrogen and oxygen in our atmosphere. And every living being, plants and animals, have some of that radioactive carbon-14 in our body. And it has what we are going to call a half-life of 5,730 years. It emits a negative electron and turns back to nitrogen-14. Remember that it's a cosmic radiation coming from the rest of the universe that interacts basically with nitrogen-14 in the atmosphere. And because that half-life is within the age that anthropologists are interested in, the decay of, or the radioactive decay of 5,730 years of carbon-14 has developed a technique that we call carbon dating. And basically, by measuring the amount of radioactivity in carbon, we'll study that when we study the process of radioactivity. You can measure the age of any artifact that you find, say, in archaeological kind of research, like a piece of wood or charcoal from a fire. It can be analyzed as of its carbon-14 content, whatever has not decayed yet, and we can determine the age of the sample of a mummy or a burial of ancient burial. So here we have two elements that are of concern or interest for us in the case of nuclear energy generation. Another one, let's look at the neutron that I suggested to you, is an interesting element in atomic mass units. Now remember that we are going to use as a reference later on the carbon-12 isotope. Why? Because, of course, organic matter containing carbon in that case is very common. The atomic mass of the neutron is 1.0086 atomic mass units. And look at this here. Half-life is 10.4 minutes, meaning that the neutron, a free neutron, is unstable. It decays. It turns through radioactivity into emitting a beta particle and turn back into hydrogen. So that is a free neutron. But a bound neutron in our body or anything around us is stable. Again, as I said, that's a secret of the holy grail of nuclear research. Why is it that the neutron, when it's free, is radioactive, but it is stable when it is bound? Another interesting isotope is boron. Boron contains two isotopes in nature, boron-10 and boron-11. And boron-10 has a property that it absorbs neutrons very strongly. So it is used in the control rods of nuclear reactors to absorb neutrons. And in that case, the scram process, when we insert control rods in nuclear reactors, that can contain that boron-10. Boron-10 also can be used in nuclear medicine. If you inject the boron-10 into a tumor, then irradiated with neutrons, it fissions into 2 alpha particles, and in that case, it can destroy the tumor cells. So in that case, it has a use in nuclear medicine as well as the control rods of nuclear reactors. We have other elements that are of interest. For instance, we can think about, let's say, sodium or titanium or chlorine. I'll send you fluorine is going to be used in the enrichment process. And notice something interesting, that there are some elements that have only one single isotope, and fluorine 19 in nature doesn't have many isotopes. It has a single isotope, fluorine 19. There are many artificial created fluorine isotopes, but fluorine 19 having a single isotope allows us to use it for the separation of the atoms of nuclei of uranium-235 from the atoms of uranium-238 and 234 when we create a compound, uranium hexafluoride, UF6, and separate or the enrichment process of different elements. We'll come back to this later on. So this is an element that's very important in the production of nuclear power. Let me see here whether I can look at another element of interest. Plutonium would be one, and that would have an element, the atomic number plutonium is 94. It has 2 more elements. Now, plutonium 94, as you could see here, doesn't have any isotopes in nature. It's all artificially created, from plutonium-238 to plutonium-239 here. This is the one that is used primarily in nuclear devices. 238 has very interesting properties. It's a very strong alpha emitter, so the alpha particles would heat any material that is made out of plutonium 238, and plutonium-238 from that perspective is used by NASA in probes to Mars or different parts of the solar system, because then that heat would keep the batteries that are used to store energy, say solar energy, from freezing in the cold of space or on Mars. And the probes on Mars right now use plutonium-238. The heat is converted into electricity, and it provides electricity rather than solar panels or photovoltaics, because of the fact that the Mars atmosphere is very dusty. So probes there that use solar electricity would be covered with dust very quickly. So the use of 238, which generates alpha particles, that is the source of heat. Now the half-life is 87.7 years. So in that case, a practical lifetime for probes using plutonium-238 by NASA in space is maybe 20 years, where you can produce electricity from the radioactive decay. So you see here that now we are talking about radioactivity also being able to produce power for us from the process of using radioactive isotopes. So in that case, a chart of the nuclides as shown here, or table of the nuclides, and I use the previous versions because it is very well developed. And you can go and try the other ones, but to solve today's assignment. So let's go look quickly at today's assignment. That basically means that you are going to practice getting mining for data from the data warehouses. That is a terminology of the nuclear age, in fact, or even in the field of renewables, we have to find that data for ourselves. So today's assignment, this is, I'm going to try to find where the list of the assignments. You can get a list of assignments in the Word format or in the PDF format. I'm asking you to access the chart of the nuclides, and in that case, it's a data warehouse in the parlance of the information age, and you data mine it, another terminology from the information age and identify the naturally occurring isotopes and their natural abundance, as we have done so far for uranium, you'll find that the case of fluorine, and you'll find also that an interesting other isotope of thorium, basically you find that only one single isotope of occurs in nature. Uranium has different isotopes. Carbon, as we have seen, has different isotopes. Hydrogen has two different isotopes, hydrogen and deuterium. And if that deuterium absorbs a neutron, it becomes another isotope of hydrogen, tritium. Lead is suggested and has been used in the moderation of neutrons in what's called fast reactors. Beryllium is a very good moderator as a reflector or moderator for neutrons. Lithium is going to be suggested for fusion type of application. Sodium is going to be suggested as a coolant for what we are going to call fast reactors. Boron, as we said, is a strong absorber for neutrons using control rods. And cadmium, also like boron, is a strong absorber for neutrons, so is used in the control rods. In addition, I'm asking you to calculate the speed in meters per second of neutrons for the 2 million electron volt fission neutrons, and for the 0.025 electron volt thermal neutrons. An intermediate energy of the neutrons was 10 kilo electron volts, so he applies the same approach that we use in the lecture to calculate its kinetic energy. So, and then of course our chapter is the first human reactors and birth of the nuclear age. So we go back to the chapter and in the rest of the lecture here. So we came to the point where we suggested that the United States was fearful that fission being discovered in Germany, that Germany is going to develop a device for war, a nuclear, an atomic device, basically, or an atomic bomb. And the Manhattan Project was started in the United States. Now, let's see how that process evolved. As I suggested, President Roosevelt, in that case, went to Brigadier General Leslie Grove, and he was from the Corps of Engineers. He had supervised the construction of the Pentagon building, and he was chosen to direct the effort. Here's a picture of Brigadier General Leslie Grove, and he directed the Manhattan Project. He was a smart person, but he was no scientist, so he had to go and seek the help of scientists that understood the process. He picked up a scientist from the University of California, shown here, that is Robert Oppenheimer, and they became good friends, in fact, and they took charge of the process of the United States beating Germany into developing an atomic device. Robert Oppenheimer from California liked to go horseback riding, so he would go to New Mexico and ride horses there. New Mexico is very beautiful. In the area that is named today Los Alamos, basically he chose it as a location for the project of the United States developing an atomic weapon and beating Germany to it. We'll see later that the war ended before the United States developed the atomic bomb, but the war in the Pacific region continued in Japan, and that led, unfortunately, to, of course, the use of the first atomic bombs on Japan. Now, Robert Oppenheimer basically helped Leslie Grove get many of the scientists, the best scientific body of scientists from Europe, attract them to the United States, especially those who were escaping the winds of war in the 1940s. Enrico Fermi was one of them, but other people like Hans Bethe, Leo Szilard, and many other scientists were attracted, of course, escaping the winds of war 70 years ago, which are happening back again in Europe. The Europeans like to basically get into fights around their borders and who controls what kind of border. The Manhattan Project built, of course, the Chicago pile number 1. The amounts but scientists knew that the uranium-235 isotope is the one that really undergoes fission. It's an odd-numbered isotope. But they also knew that another isotope, plutonium-239, that's also an odd-numbered isotope, can be produced by absorbing a neutron into the isotope, the more common isotope of uranium, which is uranium-238. And we'll look at the equations later on, the nuclear equations, not chemical equations, nuclear equations, where a neutron is absorbed in uranium-238, it turns into uranium-239. Uranium-239 is radioactive. It decays into neptunium-239. Neptunium-239 is radioactive. It decays through radioactivity into that plutonium-239. So the effort next after the Chicago pile number 1 and Chicago pile number 2 is to build a nuclear reactor that would produce large quantities of that plutonium-239 isotope. And it was thought that plutonium-239, and that was true, could fission in the same way as uranium-235 being an odd-numbered isotope. So in that case, that second pile was built. This is a patent of it. And you could see it has long tubes where basically you feed from one size the lumps of uranium, and they called it X10 pile. It was built at the Oak Ridge, Tennessee, and what is today the Oak Ridge National Laboratory. And the power in that case to produce gram quantities of that plutonium-239 was calculated to be not a half of a watt, 1/2 of a watt, only in the Chicago pile number 1, to the level to the 15 million watt or the 20 million watts. So in that case, they were able to produce gram quantities of that plutonium-239, another isotope that would fission with low energy or thermal neutrons. It was composed of, again, a large graphite enclosure contained in concrete to shield against radiation, and it contained tubes where you would feed from one side little lumps of uranium. The chain reaction would proceed, neutrons are produced, and they can produce plutonium-239. By pushing the little lumps, eventually they would fall to the bottom after 2 weeks of irradiation and in water. And then the water is taken, and now you have a mixture of uranium-238 and plutonium-239. These are 2 different chemical elements, so you can use chemistry to separate them from each other. Uranium has 92 electrons, plutonium has 94 electrons, so chemistry would isolate the plutonium-239 from the uranium-238. And again, the construction of that pile, 20 megawatt compared to the 1/2 watt of Chicago pile number 1, proceeded at Oak Ridge, Tennessee, because having a large power generation, you'll find that heat is generated from fission, and they had to cool it. So that reactor was air-cooled. They circulated air to cool the reactor. Chicago pile number 1 didn't need any cooling. 1/2 watt is a very small amount of energy produced. But there they went to the level of the megawatts or millions of watt production. And this is an actual picture of the graphite reactor. You could see it here. People standing in the front, that's the front of the reactor. These are the tubes there where you would feed lumps of uranium from one side to the middle, and then dump it into buckets, buckets, trays containing water, and take it to a chemical reprocessing process. And basically, it was at what was called the Clinton Engineer Works at Oak Ridge, Tennessee. Okay, but we did mention, so Leslie Grove and Oppenheimer basically proceeded in that direction. But they also knew that uranium-235 is an element that can fission by low energy neutrons. They didn't know whether plutonium is a good choice or whether uranium-235 was a good choice. So in that case, the decision was made to try both ways. And we'll see later that they hoped for one of the two processes to succeed, but interestingly enough, both processes did succeed. The X10 reactor was about 15 to 20 megawatts, again, compared to the 1.5 watt of thermal energy of Chicago Power number 1. And they needed to produce gram quantities of that plutonium-239. The X10 reactor was not enough. It was producing only gram quantities, whereas they needed kilogram quantities or thousands of grams quantities. So they went to a site that they named the site W, and basically W stood for Washington, and the site has been named the Hanford site. Right now, there is still a laboratory in the state of Washington on the West Coast. They called it the Hanford site, and in that case, the reactors produced so much energy that they needed to be cooled, and the cooling in that case came in from the Columbia River in the state of Washington. Again, the production there was to produce plutonium-239 from the isotope of uranium, uranium-238. They built not just one pile, they built several piles in the range of the 250 megawatt. Megawatt means millions of watts. So you could see the scale of the process. It was a large industrial process. It was given for the chemical company DuPont on a cost basis contract, meaning that the DuPont company took charge of carrying out all the projects for the United States government plus $1. So the company was reimbursed for all the costs plus $1. They built several reactors. They designated them as B, C, D, N, K, and F. And the first one was the 100B reactor. And this is an actual picture of those reactors. If you look here at the picture, you could see here in the background the Columbia River that was needed for the cooling of the reactor. 2/3 of the energy basically had to be rejected. They did not produce electricity. All they were doing was what's called a production reactor, producing plutonium-239 from uranium-238. And then, of course, they had to separate the plutonium-239 from the uranium-238. So this would be a chemical processing plant there that had to be done fully remotely. They used periscopes and they developed video cameras because you cannot look at the radiation emitted from the fission products from the process with a direct line of sight. Some of those reactors are shown here. They have been, of course, mothballed, except for one kept right now as basically a historic monument. It was a huge industrial process that only an industrialized nation can carry out. You cannot carry this process in a basement. So non-national groups have no way, absolutely no way of producing any of that plutonium on their own. Again, the Columbia River is shown there. Another unit, this would be a reprocessing plant. That would be the reactor itself. And today, another picture of the Columbia River and the facilities. Those facilities still exist, but they have been mothballed. This is the one of those reactors that was left for basically as a historical monument. Along the stacks, the ventilation stacks could reach 120 feet above the desert level. It's desert there, even though the Columbia River goes through it. That's a picture of the construction of one of those reactors with people on the inside of it. You could see that it was an extension of the X10 reactor with a graphite moderation. The fuel was uranium and uranium metal and uranium dioxide. And however, they could not just use air for cooling the reactors anymore. So they had to cool it with water. So they used tubes of water to cool the reactors. This is particularly the C reactor. That is the shape of the reactor looking from the face of it. And basically, that's the N reactor. They gave them basically letter names as letters from the alphabet. And it was graphite moderated, but water cooled. You could see the tubes of water here on the face of the reactor. Same principle as the X10, but on a larger scale. And it gives you here an idea what it looked like, the face of it. In that case, water cooling was used. And the fascinating thing is that here are the cooling tubes here shown on the face of it. So it was a nightmare in terms of plumbing. The water cooling channels shown there. Only one is used, and then the fuel was stored underwater. Water is a very good shield against radiation. So that is the front and the back face, black faces of the B reactor, with the fuel here stored underwater. It took the shape of concentric cylinders. The fascinating thing is that those reactors were very successful in producing that plutonium-239, and they were supplemented by chemical separation plants. This is one of them. Another one, the top of them here is concrete, about 10 to 15 feet in thickness to shield against radiation. The process of the chemical process of separating plutonium with an atomic number of 94 from the uranium atomic number 92, that's a chemical process using different, first they had to cut the fuel all remotely, then they had to dissolve it in nitric acid and follow solvent extraction processes to separate the plutonium from the uranium. And this is a picture from the top showing us the, here you could see the processing vessels, all a nightmare of tubing. It had to all be done remotely, as I said, using periscopes and using video cameras, in fact, were invented for that purpose. If you look here, follow the arrow, you could see that is a reaction kind of vessel where the chemical reactions and are done on the irradiated uranium-238 from the piles. The size of this processing plants was huge. This is again another view from the top. All of it done with remote control. The size was so large that they call them canyons, and they are the size of the Queen, one of the Queen Elizabeth's ships. That was all controlled remotely, and this is the control room of the canyon now. Canyon is where the processing plants are. F control room. Enough plutonium was produced to basically be tested. I'll show you the test as we go along further. And then some was left and was used on the city of Nagasaki. The other process, as I suggested, or other possibility was to use uranium-235. Now, uranium-235 is an isotope of uranium. So its atomic number is 92. And we just seen in the chart of the nuclides that uranium has two major isotopes, uranium-238, uranium-235, and uranium-234. You cannot separate uranium in that case chemically, because it has the same number of electrons for 235 and 238. So they had to develop a process that uses a physical properties of those isotopes. And that was done at what was called the Site X, again at the Oak Ridge National Laboratory today at Tennessee. And what was used is a property of charged particles when they interact in a magnetic field. In a magnetic field, in what's called the Lorentz equation in the UK and the United States terminology, or the French like to call it the Joule equation rather than the Lorentz equation. If you have a charged particle in a magnetic field, it rotates around the magnetic field lines, as we'll see in a moment. And as it rotates, the radius of rotation depends on the mass of the particle. So in that case, you separate the particles of or nuclei of uranium-235 from the nuclei of uranium-238 by the radius that they rotate, or what's called the gyro radius in a magnetic field. So in that case, two large devices were built. One is, I called it the alpha track device, where you have magnets here, and uranium as uranium chloride ions were injected into the magnetic field, and depending on the radius that they took, they can be collected at different radii, separating uranium-235 from uranium-238. The process in the magnets, of course, you create a magnet by having a current circulate in a coil. The best material you could use is maybe copper. Copper was in short supply during the Second World War, so they had to go and Fort Knox, where the strategic stockpile of the United States is guarded by the division of tank division. And Fort Knox, as you know, is where even a copy of the copy of the Constitution or the treasures of the United States are stored. They borrowed silver from Fort Knox and used it here in the bus bar, distributing the energy to all those magnets where uranium chloride was injected. Now, in that case, you would have different masses of the isotopes, and you can separate the uranium-235 from the uranium-238. That did not produce much energy, so they built another one. I could see again the magnets right here. They called it the beta track, and the name for it is a calitron. Calitron stands for California cyclotron, an invention by scientist Lawrence, and I think the physics department has a little replica that you can visit in their hallway. These two devices produced gram quantities of uranium-235. They were used for experiments. They were not really very productive in producing enough quantities of uranium-235, but General Leslie Grove kept the projects going. In his memoir, he calls them White Elephant. He knew that the Russians were spying on the United States in terms of these types of experiments. He kept it running to get the Russians, send them on the wrong track. And here is on the inside of these large calitrons, on the inside part here, they had young ladies here controlling the currents in each one of those magnets. You could see them sitting here. They call them the atomic girls. Here is a technician now working on the magnet. You could see here how large those magnet coils are, shaping them into the shape of a D. And here is the magnet coils again. It was an industrial process. And after 14,000 tons of silver bars were borrowed from Fort Knox, they were returned back after the Second World War in general. So that one was not very successful, but it produced gram quantities for experimentation. The real thing that was very successful is a third process or a second process in terms of separating the uranium-235 from uranium-238 in what is called the gaseous diffusion. And we'll describe it later on. In that case, uranium hexafluoride. Remember fluorine? We did mention a few minutes earlier that fluorine has a single isotope in nature, fluorine-19. So if you create a gas, uranium hexafluoride, it will have only the F16 atom, but the some of the molecules would be uranium-235 hexafluoride, and some would be uranium-238 hexafluoride. So you put this through what's called the gaseous diffusion process that we'll describe as we proceed further. It was a plant in the length of 1 mile. 1 mile in length. Imagine all that effort being put into it. That was what's called the K25 gaseous diffusion plant. If you visit Oak Ridge, Tennessee, I think you can visit those areas, maybe part of those areas. This one was named the Y12 electromagnetic plant. Both of them are used for other purposes now, the buildings for storage, in fact. But the K25 used the process of gaseous diffusion and was able to separate significant amounts of uranium-235, and that the uranium-235 was used in the Hiroshima device. These are some of the cells. You see how large they are here, of diffusion cells, where the in that case uranium hexafluoride is 235 isotope is separated from the uranium hexafluoride 238 isotope. Look at the size of this single cell, and there were thousands of those cells in that K25 plant, and that one was huge in size. You end up now with uranium separated, and in that case, the process is designated as enriching the uranium from what we mentioned in the chart of the nuclide as being 0.72% uranium-235 in nature to the level of 93 or 95% uranium-235. And in that case, that uranium-235 can be used into a nuclear device. And the first nuclear device using uranium-235 was used on Hiroshima in the Second World War. It was not used on Germany, where the paranoia and the fear was that the Germans will develop a nuclear weapon. It was used on Japan because Germany had basically ended the war by surrendering. The war proceeded in the Pacific, so the United States had to end the war. Some arguments were done against using the weapons and demonstrating their effects, but the argument was one to use them, and historians are still debating the process. The uranium hexafluoride that is left after separating the uranium-235 hexafluoride is stored in those big tanks, stainless steel tanks, maybe waiting for an application where you can turn that uranium-238 into plutonium-239 and then burn the uranium-239 as a source of fuel in our future in what we are going to be calling breeder reactors. This is the hexafluoride tanks, and this would be now the uranium where that stored again as hexafluoride gas in those tanks, and it is now called depleted uranium. It's not driving under the influence. That is depleted uranium. Depleted uranium, we'll discuss that later, has been used also in applications in war, because uranium has a very high density, so it can become a projectile at a density of 18.9 grams per cc. It can penetrate any kind of steel enclosure, like the walls of a tank. Steel has a density of 8 grams per cc. So if you use a projectile made out of uranium, the depleted uranium, in that case, the waste from the process of enriching it, the 18.9 gram per centimeter cube acts like a saw cutting wood. So the depleted uranium has been used as starting in the Kosovo wars and the Iraqi war, and you hear about the British supplying the Ukrainians and the United States with those depleted uranium munitions, anti-tank weapons. They also can be used as a shield in maybe soldier carriers. The back of it would be made out of a door made out of depleted uranium, so that would resist any impacts from steel or explosive devices. So it has another use other than its use in nuclear devices or in weapons. We suggested that there were 2 sites built by Leslie Grove and Robert Oppenheimer The site W was in the state of Washington, the Hanford Laboratory, and the other one, the site X at Oak Ridge, Tennessee, where the gaseous diffusion and the Calitron processes were tried. Now, the fascinating thing is that both approaches using plutonium-239 and uranium-235 succeeded. Leslie Grove and Oppenheimer thought that only one maybe will succeed, but both of them succeeded. So now the uranium-235 and the plutonium-239 were sent to New Mexico and the site that was designated as Site Y, and that is what's today the Los Alamos National Laboratory, to put that material together, manipulate it, and turn it into a nuclear device. Plutonium-239 had a property in which some amount of the isotope plutonium-240 is produced at the same time as the 239, and they're very hard to separate from each other. So the plutonium-240 undergoes a process called spontaneous fission. And if you have spontaneous fission in a device before you attain a critical mass by compressing the plutonium, in that case it's called the implosion process, could fizzle the device. So they had to test the plutonium device before putting it into a weapon. They were not sure it's going to work. But as I said, both the plutonium-239 and the uranium-235 shown here were successful. This is an enriched uranium ingot, 235, and this is a plutonium, basically puck. Think about a puck. And now you notice that it is not spherical in shape, it's flat in shape, because the sphere has the least surface to volume ratio of all the geometric objects. So in that case, spherical shape would have the least amount of material to create what we are going to call a critical mass. If you flatten it in the shape of a puck or a plate like this, the surface to volume ratio is high, so the neutrons escape from the surface, and in that case, you need a much larger amount to create a critical mass. That little mass here cannot be a critical mass. Notice that at the time they are produced, the plutonium and the uranium are not very highly radioactive. They can be held basically with gloves, and those gloves protect the metal from, say, sweat or grease from the hands into the metal itself. However, as you store it, they become radioactive, and over time, they basically can be harmful if not kept at a distance and shielded in that case. All right, so now this is basically the situation after after Germany basically surrendered. Quote the diary of President Harry Truman. President Roosevelt had died at the time, and the responsibility of using or not using the devices fell into the hands of President Harry Truman. And the quote here: "We have discovered the most terrible bomb in the history of the world. It may be the fire destruction prophesied in the Euphrates Valley era after Noah and his fabulous ark. This weapon is to be used against Japan." Why? Germany had surrendered. "We will use it so that military objective and soldiers and sailors are the target and not women and children, even if the Japs are savages, ruthless, merciless, and fanatic." Well, unfortunately, that was the situation at the time. Now, Japan and the United States are good friends, allies, in fact. We, as a leader of the world of the common welfare, cannot drop that terrible bomb on the old capital or the new. The target would be purely military one. So some suggestion was made that Japan should be warned to end the war in the Pacific because of the discovery of the atomic bomb. Now, basically, there were leaflets dropped on Japan cities warning them about the use of the atomic bomb. Because the plutonium was not really guaranteed to work right, they had to be the plutonium bomb, and there was enough plutonium available, had to be tested in what was called the Trinity test. Leo Szilard now, ironically, found himself, as he with Albert Einstein had suggested the creation of the Manhattan Project, he found himself going to scientists and writing another letter. In that case, it suggested the basically demonstration of the power of that atomic bomb signed by many scientists that has been declassified. As you could see here, it's not classified anymore, but suggesting, demonstrating the process. Arguments went on, and the group that suggested the ending the war by using the atomic bomb on Japan prevailed. For the plutonium device, you cannot get a critical mass easily because of the presence of the isotope plutonium-240. So they had to implode the plutonium, increase its density, surrounded by temper, and then a little ping pong ball there where a little amount of polonium-210 produced in a particle accelerator would interact with, on the other side of the ping pong ball, with beryllium. So an alpha beryllium reaction would generate neutrons that would start the fission reaction once that plutonium surrounded by temper, steel or uranium or lead have been imploded by those explosive lenses. So you get a sphere here of plutonium with explosive lenses. The implosion process would bring in those nuclei together by imploding them. And in that case, it had to be tested. They were not sure that that approach will work. And this is a replica of an implosion device. This would be the explosive lenses, as they are called. That would be the interior of the plutonium-239 with a levitated source at the center. And they had to raise it over a tower, as you could see here, with all the initiators put together at the last moment. They had all to be exploded or initiated at the same time. And at the top of the tower, basically in the desert of New Mexico, this would be the initiators here on top of the tower. It was tested in almost an experiment, really. These are all photographs of the Trinity device. The name Trinity was used by Robert Oppenheimer. They had 32 initiators around them. This is a replica of that device in a museum in New Mexico. And basically, it was tested and it was a success. That is the Trinity test at 0.01 second into the explosion. The reason they placed it on a tower is that they use a process of reflection. You get the shock wave reflecting, and then like if you throw a pebble in a pond, you get waves, and the ones that hit the boundary at the surface here reflect back and reinforce the incoming shock wave, and both of them propagate horizontally, so they become very destructive on structures and buildings. The fission release would generate lots of heat, so it ionizes the air. You end up with a huge ball of fire about 100 meters in diameter at 0.01 second into the explosion. And this process of reinforcing the incoming wave with a reflected wave is called the Mach stem that propagates now horizontally. The fireball goes up mixed with sucking dust from the ground, and it goes into some kind of a toroid. The gases rise to the atmosphere, but that dust here from the ground now is highly radioactive because it has been affected by neutrons. And of course, you get a fallout of a cloud of radioactivity. That happened on July 16th, 1945 at 5:30 a.m., very close to dawn. And it was a success. And of course, the end result was that it was used on the uranium-235 device, use what's called the gun barrel concept. It was easy to use. It didn't invoke any kind of testing by bringing in two subcritical masses of uranium-235 into each other in a gun barrel concept. It was given the name Little Boy as a code name. And the plutonium-239, there was enough plutonium left, and it was used on Nagasaki. But that was a test, the Trinity test for the plutonium-239. The critical mass of uranium-235 is larger than the critical mass of plutonium-239, so it's more expensive. In that case, most of the weapons today use plutonium-239 rather than uranium-235. Very quickly, we want to see here how much energy is apportioned in a nuclear fission process. We said that in that case, the mass of the uranium-235 in the initial reactants, when you create a critical mass, is more than the mass after the reaction. The fission products that come in from the fission process carry now kinetic energy. How much kinetic energy? The fission fragments of the fission process carry 165 million electron volt of energy. Gamma radiation is emitted, 7 million electron volt. The fission neutrons, 5 million electron volt. The beta particles from the fission process, 7. The delayed gamma rays from fission, 6. And an interesting aspect of nuclear fission is that those beta particles that are emitted here are associated with the emission of anti-neutrinos. Anti-neutrinos are very tiny particles, but they do carry 10 million electron volts out of that 200 million electron volt total. Now, anti-neutrinos are particles that can penetrate the Earth from one side to the other without interacting, so they're not really available for the energy production process. So we usually subtract from the 200 million electron volt fission release per fission event this unavailable anti-neutrino energy, and we calculate that fission energy event produces 180 million electron volt of energy, and that is used in the calculation, say, for the power of a nuclear reactor. In the case of nuclear devices, we measure the energy release in terms of TNT equivalent, and TNT is trinitro-toluene. This is a reaction when you explode the explosive TNT. You generate carbon monoxide, it generates hydrogen, nitrogen, and carbon. And 1,000 tons of TNT produces for us about basically 10 to the 12 calories. And that, if you translate that into mass in energy equivalent, that is a fission of just 56.8 grams of fissile nuclei, or that's 2 ounces, which is a large number of nuclei. In fact, 1.45, 10 to the 23rd fissile nuclei. The weapons that were dropped on Hiroshima and Nagasaki were in the range of 10 to 20 kilotons of. So you could see how much energy was released, but at the expense of very, very, very tiny amounts of masses. And the comparison here that we have to bear in mind between chemical reactions and nuclear processes is that a single fission event produces 180 million electron volt of energy, 180 million. Whereas the fire, which would be the equivalent to the ionization energy of the hydrogen atom, or chemical processes in general, is only 13.6 electron volt. So it's, you could see that the energy density in mass or nuclear processes far exceeds what we get from any kind of chemical reaction. And those both the uranium-235 approach and plutonium-239 approach succeeded. We'll describe in the next lecture how they were used in ending the war in the Pacific and the end of the Second World War. I have to stop here, stop sharing, but I'll remain in the chat room for any person who has any questions, answering questions. I hope that if you had questions during the lecture, that Alvaro was able to help you in that case. So let me see here. Where is the, let me close this one. I have lost the connection here somehow. I cannot find the chat room. Is Alvaro present there to help with the chat room? Oh, again, I cannot get to the. Oh, here it is. Let me see the questions in the chat room. Grant Davis, thank you for being the first person here. Why don't we consider carbon-14 as naturally occurring? It doesn't occur in nature. It comes out from the interaction of cosmic radiation with the nitrogen in the atmosphere. So in that case, it is not there present in nature until that reaction occurs. But you're right, it is naturally occurring because it happens from cosmic radiation, but it is not. It is not in just plain carbon-12. It has to come from the neutrons produced from cosmic radiation interacting with the Earth's atmosphere. So it's just a terminology, but yes, it is a natural process, but it is not available initially in the carbon-12 without those cosmic ray interaction with nitrogen. How do we submit the homework? In the page on the homework, you are asked to submit it to the Canvas site. You go to the Canvas site, you are registered for the course, you submit the homework, and the Canvas site will show you how to do it, and our wonderful TA Alvaro will also show you. You have his email in that case. Oh, okay, Alvaro answered you here, I hope. I don't know how to get more. They changed the situation with Zoom to a great degree. I have to stop recording here.